So, I will discuss today on small signal control, very important topic, and this is the fundamental, the crux of the whole thing. And if you understand this, then you should be able to do control design for any system. See, most of the system that we look at, that we want to design a controller for, are not linear, right? They are nonlinear systems, uncertain in the sense that we do not know much about it, we have not modeled it properly, or we have not modeled it completely. We cannot model it completely because we understand it less than what it actually is. So, therefore, when you design a controller for a plant, you think you know something about the plant and you have a mathematical representation for the plant, and then you try to use that one for designing the controller. Most of your control theory is for linear time invariant system, especially the classical theory, right. All take for example transfer function. How is the transfer function defined? You talk the Laplace transform of the output by the Laplace transform of the input for a linear time invariant system. But where do you find a linear time invariant system in practice? Okay. So, you make that assumption, plus you also make the assumption transfer function block, it is a block, right. It is having let us say an output and an input. Not only it is a linear time invariant system, it is having R naught of what? And Ri, right. This is 0, output impedance is 0, very ideal, input impedance is again very ideal. These things do not happen. So, most of the time what we do, we go like this, we make block diagram algebra and all those things, then we arrive at some number and we plug in the number, it will not work. Then you start trial and error. You could as well have started trial and error right from the beginning and try to design the controller. So, we want to go as far as possible towards a much more formal way of designing the controller. When you design the controller, it should work. If not the first iteration, the second iteration, third iteration, it should improve and work. And it should as far as possible represent the physical system that you are intending to control. That is very, very important. So, let us say you would have seen this. Okay, let me draw the axis. Let us say the x axis is the input, I will call it as x axis, and the y axis some output y, and we expect for an LTI system a very nice input output relationship like that, right. And we will say we have an operating point. We want to set the system such that it operates at a particular operating point. This has a slope k, and you have a nice relationship y is equal to kx, and we say linear system, very well amenable to controller design, controller theory. But if you say a practical system, take for example, I have seen this. Are you familiar with this? Okay, I will draw at least the virgin. You also have hysteresis. Typical, and you will say operating point somewhere. It could be here or it could be at the knee, no longer linear. So, like that you take any component. Take for example, you are familiar with this, very typical, your transistor transfer characteristic, right, VBE, you could have IB or even IC. All these are input output relationships or x axis y axis relationship which do not fall into this category, and most of the time it will not fall into this category, right. Most of the time your y will be f of x. What does it mean? I will have this x axis variable and I have y axis variable, and let us say you have something which is not a straight line, which is not linear, and your system has to operate somewhere there. And I will say this is the nominal operating point, I will say uppercase X, and this is the nominal output, uppercase Y. Y of course is f of x. So, to get any y, of course you could solve from the physical model, but you could also use the Taylor series approximation. Okay. What does it says? Taylor series, I will take the nominal value of x, okay, plus and so on, isn't it? This is the Taylor series approximation for that, for any such curve. You can go to any number of order, it is like a curve fitting algorithm. What is delta x? Delta x is a small deviation in the neighborhood of the operating point. So, if I take for example operating point, I will say it can deviate a bit out of the operating point on that side, can deviate a bit out of the operating point on this side, isn't it. So, there is a zone, a very small zone which I can keep on making it as close as possible towards 0 in the neighborhood of the operating point, where I can make it so small that it can be considered as linear there, right. So, I will say let us say delta x is on one side, delta x, delta y, okay, from the operating point. Deviation from the operating point I will say as delta x, so that I can represent this axis variables as x, which is equal to operating point plus delta x, and likewise this as f of operating point plus delta y. Deviations about the operating point. Now, if I start making the deviation about the operating point, if I take this neighborhood smaller, then this square terms, cube terms, fourth order and higher order terms I will remove. Approximation, further approximation. What I am saying, it is valid in that neighborhood. So, this is nothing but see y minus this is y minus the result due to the operating point is this one, I will say is some k delta x or delta y is equal to k delta x. So, whatever may be the system, nonlinear or otherwise, if I consider small signals in the neighborhood of the operating point, that is the crucial point you should note, then I can make a linear system out of it. And that is the principle that we want to use for our control also. Now, how do we apply this to our control architecture? Okay. Let us have a look at that. So, you are familiar with this, right? This is the plant, our formulation which we did in the last class. Now, let us put in these variables such that we will be able to make it amenable to the Taylor series approximation that we did, u and y. What is u? U is the control input, y is the output, sensed output. So, let us take some system, some arbitrary system, you do not need to worry right now about that one. We have the control input connected here and sensing the output. Now, this u and y, we will plot it in this fashion, let us say for example, and we will obtain some graph. It could be some nonlinear thing, need not be a straight line. Okay. So, the control input is the x axis, the controlled output or the sensed output here in this case is the y axis, imagine it in that fashion, and we have the operating point, and the operating point we will define it as uppercase. So, always remember uppercase will denote steady state operating point, okay, and the deviations will be indicated by delta the variable, or later on we will use the term, we will use the symbol hat, the variable hat on top like this. So, if I want to represent a variable x, so I will say it is composed of two parts. One is the steady state operating point or the nominal operating point plus x hat. Okay. This actually is same as what we have been using, x plus delta x, but writing delta x can be a bit troublesome, not troublesome in the sense that it is consuming more space in the horizontal domain. So, therefore, this is normally used, but we will also use that later, but right now for explanation I am going to use delta x. So, in the neighborhood of the operating point I am showing a region, so wide region in this case here, and that is the zone of operation. So, which means that your system should operate only in that zone. The moment it starts going out of that zone, you will have to change the operating point and then consider another zone equivalent small delta x zone in the neighborhood of that new operating point. So, what is delta x? Delta u? Delta u will be one deviation either up or below along the u axis, and along the y axis also you have the deviation about the operating point, okay, delta y. And of course, we saw that the Taylor series, it is in this case u instead of x, f of u, and this portion, the higher order terms, we will neglect that when you consider it small and small, when you consider the deviation as small and small, and that is given as delta y here equals k into delta u. So, this is the small signal approximation to our system. Now, how do you include it into the control structure? Okay. So, let us see this linearization. Why do we call it also linearization? Because you see that you have reduced it to this form, right, k, which is a fixed slope into delta x. Okay. Nonlinear form has been brought into this structure, therefore you say linearization. Small signal control, because the controller is only going to control deviations, not the entire signal x. It is only interested in this. So, let us form the control structure. This you are familiar with. So, we will place a controller CTL in this fashion. Now, this is the normal control structure that we see. Now, let us put in the variables. Now, this is y, right, and y is uppercase Y. This is the nominal steady state operating value plus delta y. What should be this? What is this? What should I set this? It is your desire, what you want it to be.
Capital Y.
Exactly, capital Y, isn't it? You want U, Y, just remember this, some input output, this one. You want this operating point. So, in the steady state, I expect everything will be just this. Whenever there is a disturbance, it moves away from that and then comes back to it. So, I will set that here. What is this? The error. Error is basically this portion. So, this minus this, and what will be this output? What variable will you associate for the output?
Delta U.
But this is the control input. It is complete U, right? Because there is, you have to give to the controller, let us say whatever is the Y, I have to give the complete U, then only it will reach this Y, right? And I do not have any other mechanism here, this is a straight line. So, this has to be U. So, it is the job of the controller to develop that voltage or current or whatever the control signal full U. This is large signal. Okay. So, this control structure, as you would see, very common, right? You would have seen these control structures. This CTL would just have been a PI controller, or it would be a proportional controller or a PID controller, output of which it would have integrated, accumulated, and it will give you a signal, and that signal is a large signal. It is a large signal control. But that is not what we want to do. We want our controller structure to be applicable to any system. So, we will split this. So, I will put something there in between, a summer block. So, what will be this variable and this variable? This is U, the summed up block is U, what should be this and what should be this? So, output of the controller should be delta U, and here should be the uppercase nominal operating point. So, the nominal operating point is given as a feed forward term. Deviations about the nominal is provided by the controller. So, you see the interesting difference here is that the controller is going to only operate on small signals. So, the stress on the controller is much lower, and to reach its steady state, the times taken will be smaller. So, the dynamics also will improve, and apart from that, more importantly, you are trying to give a linearized approximation. So, this will be a linear control, small signal control, very important there. Okay. So, this is the concept that we will be using. Now, this is not actually the complete control block diagram that we will be implementing, let us go towards the implementable control block diagram using this concept as the background. So, this portion here is the small signal controller. This controller CTL along with this
Sir, that
difference.
forward is always applicable.
Always. So, this structure is a structure that, see, one structure is to go in this fashion, this structure. But if you want to make this as a small signal controller, you have to go for this structure. Okay? It is important that you maintain that structure. You have to give feed forward for all your controllers if you want to have it as a small signal controller. But in some of the plants themselves are linear, or you know that you are operating from 0 to a range, where from the 0 to range it is a linear system, like say DC motor. The DC motor is a linear system where the back EMF EB is K times omega K. K is a constant fixed, and the torque produced is K times IA, again K. So, you see that it is a linear system from 0 to some operating point. Maybe beyond that, if you go, saturations and other non-linearity issues may set in. But in a region where it is defined 0 to some max U max or X max, it is linear. In such cases, you need not use this, where that U will be a 0 value, the uppercase U will be 0. So, this will automatically vanish. But in principle, you should put that so that you remember that you have to put it, you have to have a feed forward term. So, the moment you use dynamical systems which are not linear and where you want to operate it within a very specific region, induction motor and things like that one, you need to put the feed forward term, otherwise it will not be fast, and also the stress and the strain on the controller is very large, and to design for that is difficult, and it will suffer from the dynamics, it will suffer from speed, and therefore. Okay. So, so this is the small signal control structure that we will try to make it more generic. So, generic small signal control topology. So, this what we are going to put down here is what we will ultimately implement. Plant as such, as usual, you are familiar with that. Now, I am going to feed back the sensed outputs. You have this comparator. Now, I have replaced it with a gain block K, regular control. See, in the case of a transfer function based control, this K here is a dynamic block, K here is a function of omega. In the case of just output control, output feedback control, also K can be a function of omega. But in the case of full state feedback control, K is purely a gain. That is one advantage of full state feedback you can have, where K is like your proportional controller. In a proportional controller, you just put a gain, right? Like that, full state feedback, whatever may be the complexity of the plant, whatever may be the order of this plant, whatever may be the non-linearities, this will just be a pure gain. If it is a single input, single output. If it is a multiple input, multiple output, it will be multiple gains. If I am having 3 states in this plant, it's a third order plant, 3 states, then this will be 3 gains.
So, what is meant by full state control?
All the states are fed back. Now, let us say you are having a DC motor. What are the states? Let us say you have a DC motor, shaft, some inertia. There is some inertia J, this is rotating with some omega. You are applying a voltage here, RA, LA, this is back EMF EB. How many states are there? How many state variables are there? This is a storage element, okay, if you look at it in the macro. So, therefore, the current flowing through that IA is a state variable. There is another storage element here in the mechanical domain, J, it is an inertial element. So, it is rotating. So, it is storing energy by virtue of the kinetic energy of rotation. So, this will be half j omega square, this is half L I square, half j omega square. They all will be in every domain, it will be similar, depends upon whether it is potential storage or kinetic storage. Potential storage here is half C V square, kinetic storage half L I square in this electrical domain. In the mechanical rotational domain also similar, omega is equivalent something like your flow here, the current. So, half j omega square. So, omega will be another state variable, energy storage. So, it is a two state variable system. So, when I make the controller for that, K will be having K1, K2, let us say it is a matrix, it will have K1 and K2, two numbers, one for each state variables. You will be feeding back IA and omega. So, what you feed back here is not one single line, it is a bunch of lines depending upon the number of states. If we take for example, a induction motor. So, if we take an induction machine, what are the state variables? For 3-phase induction machine, let us say I am having a shaft. Okay. So, it has, I will just list down because you may or may not note the model. I will say IS, all clubbed together, I will just say one composite vector, I will say IS, because it is flowing through the primary side or the stator side inductances. That is again energy storage. So, this is composed, can be decomposed into IA, A phase, B phase, C phase. Okay. Together I am saying IA, because they are tightly coupled, A, B, C are tightly coupled. If I know one, I will be able to. I could have rotor currents, a vector, or I could have the flux of the rotor, or flux of the air gap, or flux of stator. Now, all these are tightly coupled, you can choose any one of them. Okay. If I choose IR, this is defined. So, I do not have to again choose that one. If I choose this, this is defined. Okay. So, any one of them you could choose. Then there is on the mechanical domain omega, this again is kind of connected. So, if you see this and this, so this being a vector, it is having two parts, A, D and Q, A and B. This is also having two parts, D and Q. So, 1, 2, 3, 4, 5, all 5 I will have to feed back. If I do not have any, if I have not measured any, if I have not measured the rotor currents, what will I do? I will estimate it. Okay, something that I am not having, I have to estimate it. So, I will, all measurable things I will take, let us say I measure this, I am able to measure this, I am able to measure this. These two I will estimate. So, this is estimated. What I will do, I will put them all, bunch them all together, ISD, ISQ, let us say IRD, IRQ and omega. these alone you are not able to measure. So, what you will do? You will estimate or observe. Then I will put them all together and then feed it back. So, it is still a full state feedback. Then I will have how many gains there? K1, K2, K3, K4, K5 like that. So, that way it will start falling into place. So, if I am having for example, something like this, what is this converter? Buck converter. How many states are there? How many state variables are there? In this case, I am having one energy storage element here, another energy storage element here. So, I have IL as one state variable. I have this voltage across the capacitor Vc or V naught as the other state variable. So, it will look like this. So, let us say for this case of buck converter, if you have to visualize, it should actually, if I split all these lines here, single lines into that bunch, two state variables, I have to feed back that, okay, comes there, there will be two difference stage. Then this will go to K1, K2, then again combined together, because the input is only one. It is not a two input, two output system, right. Input is still, it is a single input, output also may be single. What you are feeding back is all the states, output may be just V naught, is not it. Here it may just be V naught. The single input, single output system, right, it will go in there. Reference, so you will have a reference finally should be V naught star. That is what you want, desire, isn't it. So, I should have some stage in between which will set this IL star and Vc star for that particular operating point. I know the model of the system, I will use that model of system, find out what is the steady state values, uppercase Y we saw, no. So, I should be able to give the steady state values here from the steady state model. final reference is only V naught. So, it should look in this kind of a fashion, the entire block diagram. Okay. Anyway, let us evolve towards that. All these lines that I am showing are not single signal lines, they are multiple lines, you should remember that. So, it can be single input, single output, it may be multiple input, multiple outputs, okay. No issue. K here is can be scalar or can be a vector, but you imagine it as multiple values of K, depends upon how many states are there. Okay. Okay. Now, let us put in the values here. Now, this y here, so actually you should imagine like this y, this is y, right. So, y equals a vector like this. Pardon me? This is what I am feeding back, right?
No, X or Y. Y is for output. Okay. No, nothing, sir.
Here, the sensed output, I am using that one as the sensed output.
Right.
This is also sometimes called Z in the literature. Okay. The controlled output, the one which I am using, fed back output as Y, controlled output as Z. Again, convenience. In some literature, H is used, but as long as you are clear what it is. This is the fed back signals what we are using. No hard and fast rule that you need to use it as Y. People have used Greek letters also. So, whichever is convenient to you, you can use, but be consistent, that is all. Yeah. And when you say Y is equal to this plus delta Y, okay, or Y is equal, or this is equal to Y plus Y hat. So, this is nothing but Y hat or delta Y. You are getting the feel there, okay. So, even these variables here what we are using are vectors, vectored variables, but you will get the feel for it as we start going deeper and deeper. This is our reference here, okay, and you get the error and the U. This is your large signal system. Now, I was indicating here something here, right. So, the Y here and the reference here can be different. The reference is not IL star, right. Of course, in this it turns to happen that V naught star and VC star will be the same for this particular plant because these two are common. But what Y you have here and the reference that you want can be different. It can be a scaled version algebraically multiplied with some other function. So, let us put something there. Okay. I will put one converter block here. It is not a dynamic converter, it is an algebraic equation there, which will scale this Y from a reference which is the true reference R, which I actually want to control. So, this R is actually this. You would like this to be controlled. Fine. This is fed back. Feedback need not necessarily exactly be same as this. Do you get the difference there? This is the controlled output, the output that you actually want to regulate, and this is fed-back signal. Okay. So, the feedback signal, of course, you need to have a reference, and this is a reference generator. Ny is a block, we can call it as a reference generator for this from the true reference or the controlled output reference. Clear? Very similar to this kind of a concept. V0 is actually what you want to control, but you have to generate reference internally for the feedback signals. This is a reference generator to generate this. Now, this is still large signal control. I want to make it small signal. What I have to do here? I have to put in something. I have to put in a summer. It is a feed forward point. So, this here will be delta u. Now, the controller here is small signal, what we want. Here I have to feed in u, the feed forward term, the steady state portion. Remember, how will I get u? I know the input output relationship. I had before. I have the input output relationship, steady state input output relationship from the steady state model. I have this operating point. So, if I am having u, I can get y, which is equal to f of u, or if I have y, I can get u, the inverse function of n. So, I want to give u, okay, from this reference, true reference, let us say. So, I will make a connection here. From this reference, I am going to pass through ny reference generator, generate the reference, internal reference. From this reference, I will pass through another block nu to generate u, because you have to make them compatible. See, u can be duty cycle, this can be voltage. I cannot just directly give it here, right. I have to map it to duty cycle. So, there will be a relationship. If this is the value of voltage, this should be the duty cycle. If this should be the value of output voltage, V naught min, V naught max, D min, D max I should get. So, I should have a relationship depending upon the plant. Depending upon the plant model, I will have a relationship where I will get the steady state u. Okay. For the DC-DC converter block, this would have been D, duty cycle. Fine. So, this is a small signal controller, this whole thing, small signal controller. Still, it is not complete in the sense that you remember that when we just discussed this induction motor, we had 5 states, and some of the states are not measurable. Likewise, let us say that here IL is not measurable, this here for this. Assume that we do not have sensor for that. So, I have to somehow estimate this. I will call IL estimated value. And then I will push that IL estimated value all along here for feedback. So, what I will have here would be IL estimate, this will be measured. Let us say I am not measuring either of them. You could, from some other measurements, you could estimate this also. You could estimate all the states. what you are measuring may be a some algebraic function of this, and then you should estimate this and this. Sometimes I may be measuring VC itself, but people will make a generic estimator and put all as estimators also, just to keep all those things possible. So, of course, here let us say if you are measuring, it is always good to put the measured variable, because that is the most exact, and that which I do not have, I have not put a sensor, I am not going to invest on a sensor because the sensor may be very, very costly, I will estimate it. Okay. So, you need to put an estimator there. Now, this estimator, when I say put an estimator, include an estimator there, is it another plant? Is it another system? What have I put there? I just put another flower, right? Or is it another duplicate of the plant? It is actually a virtual plant. It is an emulated. So, from the model, see, I have modeled this fellow. I know the mathematics of that. It is only that mathematics of that which is run virtually within the processor. Okay. So, you do not have to worry, it is not a physical thing which is there. I am not building another physical plant, duplicating it and then trying to estimate. It is basically the model of the actual plant which is running within the processor. Estimators are also called observers. So, in the literature, if someone says observer, it means estimator. So, it is actually estimator / observer. So, whenever we use an estimator, we try to give the same, you have the plant, it is like emulating the plant. We should give the same control input and also take the output of that. So, the estimator should also be given the same input, so that its behavior is as close as possible to, and you will take the output of the plant whatever is measured, and you will take from the estimator also the output whatever it has estimated. You will try to find out the error, and using the error there is a local feedback here, and that local feedback will have a gain G, and the output of that is the feedback that we are feeding back. Okay. So, this G is another component that we have to design and fix in. So, when you say Kalman filter, if this is a Kalman filter, it is an optimal estimator. So, the Kalman filter will have some gains that we need to find out. So, that is that gain G. So, that will be a Kalman estimator gain. Or if it is a LMS algorithm, mean square estimator, as again another filter, that will have a gain G. They are all local loops, local feedback loops. So, you need to remember this is also pure gain. So, you have a pure gain G to be estimated, then only you will get the all states. You have a K to be found out, that is the second design component. You need to find out NU and NY. So, these 4 blocks in blue, if you are able to find out, your entire system is through. And the beauty of it is there is no trial and error. These are closed form solutions. If I am having K, 4 Ks to be determined, K1, K2, K3, K4, 4 states are there, 4 Ks to be determined. I have 4 equations, 4 unknowns, K1, K2, K3, precisely you will be able to find out and plug in. Same way for G, you will be precisely able to find out and plug in. That is why I said they are 5 minutes job. In 5 minutes, G, K, NU, NY, you should be able to, 5 minutes too much. For whatever time the computer takes to compute, it will give you the values. You plug it in, it should work. Provided I have modeled this plant properly. So, the whole crux of the control, whatever be the control design that you do, how good I have modeled this plant. If I have modeled this good, then all this will work perfectly. First attempt it should work, no trial and error. But what happens is that many a times the plant is not well understood. It may be a 10th order plant, you may probably have approximated it to a 4th order plant. So, we will consider that also, and what we do is that we will place the closed loop poles where the closed loop poles of the plant should be, and we will place it within a zone. Never will we say, see, in a typical classical controller design you would have said, the plant is having this transfer function, it have a numerator, denominator, zeros, poles, all those things, numbers are there. So, when you are designing the controller, you have the controller, I will have this 0, this pole, cancel, cancel, right? You would do that, no? Have you done that or not? Isn't it? That is the wrongest thing to do. Because when the plant is running, those parameters are changing. Your time constants are changing because the resistance values are heating up, the values are changing. Probably it may be going towards the linear region of the different loading conditions, different things will happen, and those parameters are not fixed, and your controller, that cancellation will not work, because inside in your model or in the processor, the controller parameters are not changing. It is not feeling the same effects of temperature, power, loading and all those things. So, you would have cancelled it, and then under the condition of cancelling you would have got a good response, but as the plant is working, the parameters have changed, cancellation has gone off, and then everything is haywire, isn't it? Because the order of the whole system has changed. Because of the cancellation it was some order, reduced order, and as it is running from a second order it has turned to third order or probably fourth order, and then suddenly the controller is not able to manage that. So, these things will happen. So, you should always consider that cancellation will never happen, and also you should also consider that parameters will change, and therefore, your closed loop poles should be within a zone, within a region. So, you will say, let the closed loop pole move about in this region, then it will be robust, even things there's one. And even if I have not understood the plant as precisely as it is supposed to have been understood, no problem. It will be within a particular bounded region. So, that is the whole this one. So, the important takeaway from this block, very important block, this should be there in your mind all the time. This is actually what your whole entire system is, and this is what, whichever may be the plant, this is the system. Plant, estimator, G we have to find out, K we have to find out, NU we have to find out, NY we have to find out. Only 4 components we need to find out.